now let's try to look at the last subtopic of this chapter 5.5, which is about mutual inductance. So previously we learned that about self-inductance, which is involved with one circuit. Now it involved with two circuits. Okay, so let's say this is my circuit 1 and this is my circuit 2. Circuit 1 represent the primary. The primary is the one that has a power supply, and the secondary is without any power supply. Okay, but you can see that if there's a change in current over here, it will start to induce current flow over there. Okay, so even though this one doesn't have any power supply, you can see some readings in the voltmeter. So how does that happen? Okay, we are going back to our primary circuit first. Okay, so if I close this circuit, let's say this is a complete circuit, then you can expect that this solenoid in the primary circuit will produce magnetic field. Okay, and to find the direction, you have to use the right hand grip rule. Okay, since the direction of current always from the positive, goes in that direction, so over here you have current flowing in that direction. Okay, so initially you can use right hand grip rule, so your fingers is pointing towards the current direction and your thumb will be pointing to the knot. So as a result, it will produce a magnetic field in that direction. So I just make it very long over there. Okay, so that you can see that this magnetic field that is created in the primary circuit actually produced also on the secondary circuit over there. Okay, so just this one makes just redraw this one, so you can see that over here it has a magnetic field in that direction. This one is due to the primary. Okay, but now what happened when I start to change the magnitude of the current? Let's say I switch off I pull out the switch, so this one is not a complete circuit, so the current will decrease, the magnetic field will decrease. So initially you have magnetic field in that direction, now you have magnetic field induced because there's a change in magnetic flux, right? So over here we try to oppose the change. Okay, so induced magnetic field will be produced in that direction because basically they want you to oppose the change. So decrease, they want to increase again. So this is what we call induced magnetic field. Okay, and using the same right hand grip rule here, okay, I can determine the direction of induced current. So it will be, I think I blocked the inductors there, but it will be in that direction, right? So like that. Okay, just delete this one. So the direction of current will be in that direction, so induced current. So you can see that what happened here is that even though there's no power supply in the secondary circuit, because there's a change in primary circuit, okay, that result in change in flux also in secondary circuit, they have induced EMF and induced current. Okay, now for that one is for the theoretical part. Remember, this is the primary is the one with the power supply, and we call this one as first circuit, and the secondary is without the power supply, we call that one as the second circuit. Okay, to calculate the magnitude of mutual inductance. Okay, this one is from the Faraday's law. EMF is directly proportional. This one, if you notice, this one is EMF induced in the second circuit is directly proportional to the change in current that occurs in the first circuit, the primary circuit. So basically, induced in the second circuit due to the change in the primary or the first circuit. Okay, so because of that, you need to have a constant. This one is the mutual inductance. Okay, this is a negative because this indicates the direction that oppose the change. This is what we call mutual inductance. Okay, represent by the symbol M. Previously we use L, this one we use, kalau self-inductance, L, mutual inductance is M. So here again, this one is very similar equation, just that flux in 2 over I in 1. Okay, and if I do flux in 1, it will be over current in 2. Okay, so this is mutual inductance for 2 due to 1 due to 2, which is equals to M. Okay, so the magnitude of mutual inductance in, both solenoid here, because both of these interact with each other, is equals to M. We call that one just simply M lah. So this one becomes M. Just change this one. So this one becomes M, but the key thing here is that this is secondary and this is the primary. That's the key thing. Okay, as long as you understand that, it should be okay. And then instead of having mu naught n square A over L, now we have n multiplied by n. Excuse me, where n1 is the primary and n2 is the secondary. Turns in solenoid 1, turns in solenoid 2, and A and L represent the area and the length of the primary solenoid. Okay, we try to look at one example, few example. We have two questions here. This one is question 14 from the tutorial question. It says that find the current, find the coefficient of mutual inductance of the two coaxial solenoids of 5 cm radius and 30 cm long. So the radius R is equals to 5 cm, which is 0.05 meter. I can straight away calculate the area, which is equals to pi R square. So pi multiplied by 0.05 square. So I got 7.85 times 10 to the power of negative 3 meters square. The length L is 0.3 meter. I change to meter. And then if one solenoid has 10 turns and the second one has 1000 turns, so it says there here and 1 is equals to 10. Okay, normally the numbers of turns is not equal normally. So here you can imagine the previous circuit there. So using the equation of mutual inductance, M equals to mu naught N1 N2 A over L. So now it becomes 4 pi times 10 negative 7. N1 is 10, N2 is 1000. A is equal to 7.85 times 10 negative 3. And the length is equals to 0.3. Okay, so mutual inductance is still inductance, so the unit will be the same, which is Henry. So if you calculate this one, you should get 3.288 or 3.29 times 10 negative 4, and the unit is Henry. Okay, it's the scalar quantity. Okay, question number 15. It says a primary solenoid 50 cm in length has a radius of blah 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 6 cm, 500 turns, current in the flowing through a rate of 2.3 ampere per second. Okay, so you can imagine this is about the primary solenoid. So primary solenoid, maybe I can draw it over here, the two circuit. Just roughly draw it over there. So primary, we should have power supply. Okay, and this is the solenoid here. Okay, it says that the dimension, radius, this is 1, represent primary, radius is 0.06 meter. So your area here, I can straight away calculate it, pi r square, so pi 0.06 square so you should get 0.0113 meter square. Meter square. Just double check the calculation. So 0.06 square multiplied by pi 0.0, okay, correct. And the current here is equals to But remember, in this current flowing at the rates of 2.3 ampere per second, that one actually indicates di over dt. If you're not sure, you can check the unit. So you can see that the unit is ampere per second. So that means 2.3 per second. Every second 2.3 current flows. What else? Oh, that's it. Okay, so maybe I just put this one over here. Length. Did they give you the length? No, but they did give you the length and the turns. Okay, just bring this one back to this side. Okay, so length is equals to 0.5 meter and turns N1 is equals to 500 turns. Okay, so the first question they want to calculate the self-inductance in primary solenoid. So we are talking about this solenoid. Solenoid number 1, we have to solve using L. Okay, instead of M, we have L. Mu naught N square, if mutual inductance N multiplied by N, and then still A over L. Okay, so the formulas are very similar. Mu naught is 4 pi times 10 negative 7. N is 500 square multiplied by the area there, 0.0113. Okay, make sure your N got square there. Length is 0.5. Okay, so that one should be 7.0999 or 7.10 times 10 negative 3, and again the unit will be Henry. Okay, now the second part of the question, it says that the induced EMF in the secondary solenoid with 80 turns. Now it says that it actually have another circuit over here. That consists of another solenoid. And this circuit, the numbers of turn and 2 is equals to 80. So your N1 is 500. So to calculate, they ask you to calculate the induced EMF. Okay, to calculate induced EMF, you can use epsilon EMF equals to negative M over di dt. Okay, so induced EMF is equal to mutual inductance multiplied with di dt. Di dt is given 2.3 ampere per second. Notice that di dt here is from the circuit 1. Right. So you have to calculate mutual inductance first, and then you can substitute inside this formula. The mutual inductance M equals to mu naught N instead of N square A over L. So it will be 4 pi times 10 negative 7. And 1 just now is 500. And 2 is 80. Okay, you use area and L from the primary, which is 0.0113, and the length here is equals to 0.5. Okay, so the only difference here is that you change N square to N and replace with the secondary term. You calculate again. Here I got is 1 excuse me, 1.136 times 10 to the power of negative 3, and the unit will be Henry. Okay, epsilon here, values for mutual inductance M multiplied by di dt, which is equals to 2.3. Okay, the answer would be 2.61 times 10 negative 3 volt, or you can write, don't forget the negative, or you can write millivolt. 2.61 negative 2.61 millivolt. Okay.